sorry it's taken me so long to get to this. I keep getting people asking me to do things, and unfortunately that means I've had to push some things out, and I'm really sorry that you have been one of those things that's been pushed out. So I wanted to try and get to some of the questions that you've been asking about. So I wanted to start with number 22 because that's one of the things that I think we can talk about first. So I'm going to go ahead and go into the student view on Alex so we can look at this as a student. And you were talking about the matter and units of measure assignment. And I know you were asking about 22, and I know that was a specific one you had questions about. Now, I could look at the one that you were working on, but I think this will be similar enough. Oh, no, never mind. I'm gonna stop this. Hold on. Let me go back to let me pause this for just a second. Get into actually your grade, your actual thing, and I have to go through the grade book, which is why I stopped. Now I can do this. Okay, so now I'm here in your assignment that's in progress, and this has the ones that you've done. So I'm looking at your number 22. And what I see in here is the one that you were asking about, and you're saying, okay, I know that it's somewhere between 6 and 7. Clearly, it's beyond the 6. It's not quite to the 7. And you were saying that there's 1, 2, 3, 4, and then the fifth. And so, each one is 0.2, and that is correct. That is correct. So we're looking at 6, 6.2, 6.4, 6.6, 6.8, and 7. That's right. And what I'm looking at is it's not quite to the 6.8. If I draw a line straight up from the 6.8, it does not hit that. Okay. So I know it's past the 6.6. I know it's not all the way to the 6.8, and so that's why I would read that as 6.7, which is what they say that the correct answer is. And I would agree with that because it's past the 6.6. It's not all the way to the 6.8. And if it's in between those two, then it's got to be that 6.7. And that's why I would report that. Now, I would not report this as 6 point, I mean, could I guess that it's 6.70? Yeah, I could guess that, but I don't think I have enough accuracy to do that. Now, if it was exactly on that line, either one of them, then could I maybe say that it was 6.6 or 6.8? Maybe. And maybe I should be saying that it's, 6.70, 6.7, maybe. I would say that that might be more appropriate, but I can understand why they're saying they're not going to do that because I'm not entirely sure that it's exactly 6.70. So I can see why they're not saying that you should be guessing that far because you're actually guessing at the 6.7, really. I mean, because it could be 6.69, it could be 6.72. I mean, it could be anywhere in that. And so the 6.7 is a guess in and of itself. So that's why they're saying that it should be something like that. So that's the deal with 22. Okay. Um as far as the rest of them, let's go and take a look at number 3. So let's go back to 3. So when we look at 3, we're looking at a question that says, an anesthesiologist has ordered 1.2 milligrams per kilogram of IV midazolam for a 54-kilogram patient about to have a surgical procedure. The drug is to be delivered over 90 minutes. A 250 milliliter bag of normal saline in which 1 gram of midazolam has been dissolved is available. Suppose the IV pump is initially set to an infusion rate of 10 milliliters per hour and runs for 45 minutes. That's a lot of information. I get that. So I'm going to pull up my lovely piece of scratch paper if it will cooperate with me. And I'm going to go ahead and open that scratch paper so that you can see that too. Making sure I know where I am. Okay. So I am sharing my screen. This is my scratch paper that I'm looking at. To do that, I'm going to pull this over here so I can look at that, and then I'm going to pull this over here, and I want to pull this like this so that I can look at both of these. It's going to cooperate with me anyway. Come on, work with me here. Yeah, there we go. Okay. So I have a whole bunch of information, and I'm going to write that down. That's all I'm going to do at this point. So 1.2 milligrams per kilogram. 54.0 kilogram patient. The drug is to be delivered over 90 minutes. $250 milliliter IV bag of normal saline in which 1.00 grams of this has been dissolved is available. Suppose the IV pump is initially set to an infusion rate of 10 milliliters per hour. Runs for 45 minutes. Okay. So this is how long it's been running. Okay, awesome. I have a bunch of information. So I'm looking at all of this going, right, I know a bunch of stuff. Now, there are a number of ways that I can approach this, and there's no one way to do it. I look at this and I say, all right, I need to make some combinations of this information so that I can deal with what I have. And I usually work in the order that they give me the information. So I have this milligrams per kilogram, and I know that it's a 54 kilogram person. So I'm going to combine those two. And what I'm going to do is I'm going to multiply them together, because if I multiply the number of milligrams per kilogram times the number of kilograms, that'll tell me how many milligrams this person needs to have delivered to them. So I take the 1.2 milligrams per kilogram, and I multiply that by the 54.0 kilograms. And I cancel the kilograms, because when I do that multiplication, I cancel that unit. And so I know that if I do this multiplication, that will tell me how many milligrams this person requires to have given to them. Okay. So that will tell me something that I need to know. I don't know if that's everything, but it's a step in the right direction, so I'm going to do that. Okay, so let's see what happens when I multiply those together. So I take my 1.2, I multiply that by that 55.0, and that gives me 64.8. 64.8 milligrams that are required for this person to have delivered over the 90-minute time that we're looking for. Okay, so that's what's supposed to be delivered over the 90 minutes. All right. Okay, so that's supposed to be done over 90 minutes. Let's talk about how much has been delivered over the time that it's been happening. Okay, so the first thing I need to look at is how much is in the bag that we're talking about. So it's a 250 milliliter bag, and there's 1 gram in that bag. So I have 1.00 grams, and I can convert that to milligrams. So there's 1,000 grams per milligram, because that'll get me to milligrams. Okay, so 1.00. No, wrong direction. There's 1,000 milligrams of 1 gram. I did it the wrong way. 1,000 milligrams in 1 gram. And so that means that I have 1,000 milligrams, and that is in a 250 milliliter saline solution. So I know that that's in 250 milliliters. So that means that I have 4 milligrams per milliliter. Okay, so that's how many milligrams per milliliter. And I know that I'm delivering this at 10 milliliters per hour. Okay, and it's been running for 45 minutes. So I'm going to take that because I want to see how much, what volume have I delivered. So if I look at the 10 milliliters per hour and I multiply that by the 45 minutes, and I know that there are 60 at 1 hour, 60 minutes, and the hours cancel, the minutes cancel. So if I take my 10 milliliters, I multiply that by the 45 minutes, and I divide that by 60, that means I have delivered 7.5 milliliters. Okay, so that's how many milliliters I have delivered. And I know that I have, within that, I was looking at 4 milligrams per milliliter in that bag, right? So if there are 4 milligrams per milliliter, which we calculated right here, and I've done this, 7.5 milliliters has been delivered at this time, then I know that I can take that 7.5 and multiply by 4, and that means that I've currently delivered 30 milligrams to this body at this time. Now, I know I'm not done, right? I haven't delivered enough yet, which is good because I haven't overdosed them yet. That's awesome. But what I know is that they're supposed to get the 64.8 and they're only at 30. So I have the 64.8 milligrams that they should get. I can subtract out the 30 milligrams they've already gotten, and that means that we have 34.8 milligrams that they still need. Okay. And I know that we're delivering 4 milligrams per milliliter. Okay. At an infusion rate of 10 milliliters per hour. Right? So 4 milligrams per milliliter and 10 milliliters per hour. That means that I'm doing 4 milligrams per milliliter and 10 milliliters per hour, which means that I'm doing 4 times 10, 40 milligrams per hour, right? My milliliters will cancel, and that leaves you with milligrams per hour. Okay. So I know it's going to be less than an hour that I need to be doing this. Okay, that's good because that's a good thing because I've already done 45 minutes, so I only have 45 minutes left. So it better be less than that. Okay. So I need to deliver 34.8 milligrams, right? So I take my 34.8 milligrams and what I'm going to do is I'm going to divide this by this 40 milligrams per hour. Okay, so technically it's 40 milligrams per hour like this, so that we're turning this conversion factor right here over and putting it right there. Okay. That is a conversion factor. I've flipped it over to use right here so that I can figure out how many hours I need to use this to get that 34.8. So 34.8 divided by the 40, and that gives me 0.87 hours. Which 52.2 minutes of additional time. So that's what is supposed to happen. Wait a minute. Just checking. Looking at my work. So how much has the patient already received? That would be the amount that we calculated, that 34.8 milligrams. Oh, no. So how much have they already received? Is the 30 milligrams. How much do they need is the 34.8. And should the infusion rate be changed? Yes, because if we keep it at the same rate, then we're going to need 52.2 minutes, and we don't have that much time left because we only have 45 minutes left. So we need to increase it to be able to give them the right amount in the time that's left. Okay, because this 0.87, if we multiply that by 60 minutes per hour, equals 52.2 minutes. And so we have to increase the rate in order to deliver that in the 45 minutes left. So there's not one single equation that we're looking at to do this. This is a bunch of unit conversions that we're doing with the information that we've been given. And all I did was look at the numbers that I had and say, how do I combine those numbers to get rid of the units that I don't want. So I can multiply these together, and that gets rid of the kilograms and gives me milligrams. Milligrams is good because I need to know how many milligrams. There was a question, and the answer, one of the answers I needed was milligrams. So let me do that. Okay. And I know that one of those answers is going to be the total number of milligrams that are needed for this person. So that's a good thing. Now I can do another calculation to see what the number of milligrams per milliliter is. And that was this calculation that we did right here. That's how many milligrams per milliliter. And so I can look at how many milligrams or how many milliliters have been delivered and over the time frame, and do this conversion from hours to minutes to tell me what volume has been delivered. Okay. And if I know that it's 4 milligrams per milliliter times 7.5 milliliters, that means I've already given 30 milligrams. So if I know he needs 64.8 milligrams and I've only delivered 30, that means I need to give 34.8 more. And I can take that 34.8 milligrams that I still need, and I can divide it by the 40 milligrams per hour that I got from combining these, the 4 milligrams per milliliter and the 10 milliliters per hour, the current concentration, 4 milligrams per milliliter, and the current rate, the 10 milliliters per hour. And if I do that division of how much is left and what the current dosage rate is, then I see that the time that's required is more than what is available to me. And so that's why I have to do an increase in that rate. Okay. So it's a number of different calculations. And the only way I knew what to do was by looking at the units that I had. That's it. Okay. I may not understand anything. And here's the thing. I will kid you not. I didn't understand most of what I did in physics. Almost all of it. I didn't understand it. But I knew what units I needed. I knew that if I set up this particular equation, the thing that I was looking for in the end had this particular set of units. Power had this kind of units. And I can't remember most of them now because I really didn't understand them, so I can't remember. But I knew what kind of units it needed. And I could get to those units by doing dimensional analysis. And so if I could get the right units, then chances were that I had done the right calculation. And I didn't understand a damn thing. But I got the right units and I got an A in that class. Could I tell you what I did or how I did it? No, I really couldn't. I know that at one point we calculated how fast a ladder would have to be traveling for a 10-foot ladder to fit in a 7-foot barn. I know I did that calculation. And it made no sense to me because as soon as you close those doors, it wouldn't be traveling anymore. And so it would immediately not fit anymore. But I know we did the calculation. So I remember being annoyed by it, but I know I did the calculation. I remember lots of things about that, that particular part of physics pissing me off because the first day of that class, I went in and he talked about a whole bunch of things and I went, oh my God, I finally understand what they're talking about. He reviewed the last 3 quarters of physics and I understood everything he had said. And then we get to the last 5 minutes of class and he says, none of it's true. And I thought I was going to shoot myself because I was like, what are you talking about? Because that's when we started talking about relativity. And I was really frustrated. But, I could make those units work. So, this is why I tell people, pay attention to the units. And this is why I make you do these questions like this, where there's not really a simple, this is how you do it kind of way to approach it. Because I want you to be paying attention to the units. Don't think about what you're supposed to plug in or where you're supposed to plug it in. Think about the units and how do you get rid of the ones you don't want to get the ones you do. They're asking you for milligrams. How can you manipulate these numbers to get an answer in milligrams? That's all I want you to think about. And if you can do that, you'll be fine. So that was 3. Let's take a look at 5. Convert the following measurement. Okay. So I have 8.3 times 10 to the minus 5th kilograms over mole times deciliter is equal to X number of grams over mole times liters. So I need to do a number of different conversions. The moles are the same, but I need to convert from kilograms to grams and from deciliters to liters. So those are 2 different conversions. So when I go from kilograms to grams, I know that 1 kilogram, so 1 kilogram is equal to 1,000 grams. How do I know that? That's on my exam handouts. Okay, so when I come into my D2L shell, under content, course documents, exam handouts, one of the things that's on here is this thing right here. And if I zoom in on this, because I can do that right here, I can see that kilo, it's right here, and it says kilo is 1,000, meaning that there are 1,000 of the base unit in a kilo. That's what that means. So there are 1,000 grams in a kilogram. Okay. Now, the other thing I need to look at is how many deciliters are in a liter. So if I come and find deci, that's right here, and it says 1/10. So it's 10 to the negative first. So I have 1 deciliter equals, and I always do it this way. 1 liter equals 10 to the minus first. Sorry. 1 deciliter equals 10 to the minus first liters. Okay, because that's the way it's more comfortable for me. So then I can use both of those conversion factors. And the way that I do that is 8.3 times 10 to the minus 5th kilograms over mole times deciliter. And then I know that there's 1 kilogram, and that's 1,000 grams. That will cancel the kilograms and leave me with grams. Okay. And then, of course, I want to get rid of the deciliters. So 1 deciliter is equal to 10 to the minus first liters. And so that will cancel the deciliters and leave me with liters on the bottom. So I can run those happy numbers. I say 8.3 second EE to the minus 5th. And let me show you, because I have a calculator here on my screen that I can pull up. And this is a TI-84 plus CE. It's the same calculator that I manually use. So when I put this in on my calculator, it's 8.3 second EE negative 5. Because that's how you put in scientific notation on these calculators. Okay, if you do this as, I'll go ahead and enter this, but if I do this as 8.3 times 10, and then do hat negative 5, that ends up being, sometimes it's fine, sometimes it's not. And so the better habit is to do this, because sometimes this works and sometimes it doesn't. And so if you want it to always work, make sure that you do it this way. Because usually what will happen is if you have one of these on the top and one of these on the bottom, i.e. you divide, then it screws up. It doesn't do that when you do it like this. But for whatever reason, if you do a division with these in this format, something messes up. And I don't understand why that happens. It makes no sense to me. So, but all I know is that if I do it this way, each and every time, I don't see that issue. So I take this and then multiply that by 1,000. And I divide this by 1 second E I have 1. And that gets me 0.83, and that would be the number that I would enter in the ALEKS right here. 0.83, which is what it says for the correct answer. So that's the kind of thing that we're looking at. I always do it as 2 different conversions because there are 2 units that I need to change. So that's the way I would handle that. Looking at 8 mole per liter times liters. So 93 times the 40 would give me that answer there. So 93 times 40. And of course, both of those are 2 sig figs. So I would end up with 3.7. And again, worrying about sig figs and things like that. So 93 times 40. Enter. And if I'm worried about the sig figs, I can go to mode, and I want to change this from normal to scientific. So I want to use this key right here, and I want to hit enter there, and I go second quit, and I do times 1 because I want to take this answer and multiply it by 1 to get the same thing, but now it's in scientific notation. And because I only have 2 sig figs here, then I would put this in as 3.7 times 10 to the 3rd. Because that will take care of your sig figs for you. So it's 3.7 times 10 to the 3rd. Okay. Looking at the next one, 867. So 867.0 divided by the 5, 7.4. And again, lovely notation here. And I'm going to leave it in that way. I have 3 sig figs here and 4 sig figs there. The 0 wouldn't be there if it wasn't significant. So 3 sig figs, that means my answer should have 3 sig figs. So 1.51 times 10 to the 1st is how I would report that. Okay. Now you can report it as 15.1. That's fine, but I would report it as 1.51 times 10 to the 1st. Okay. For the 20.9 times 34, I end up with 7.106 E2. So again, 2 sig figs here, 3 sig figs there. I would report this as 7.1, 2 sig figs, times 10 to the 2. And again, that's, yeah, it's one of those things where 7.1 times 10 to the 2, 15.1. Again, that would be fine. And 3.7 times 10 to the 3. Because it's two sig figs. Yeah. So watching for your significant digits, that's the biggest part of that. And making sure that you're reporting it in scientific notation. So you can either report this again as 15.1 or 1.51 times 10 to the 1st. Either one should be acceptable. So there's that one. 15. So again, we have kilograms per mole deciliter. And again, this is going to be a similar conversion to what we did before. So we've got our 0.00593. This is kilograms per mole deciliter. And I'm going to do 1 kilogram down here and 1,000 grams up here. So that will cancel that. And then I have 1 times 10 to the minus first deciliters in 1 liter. Sorry. 1 times 10 to the first deciliters in 1 liter. So working that happy math. $59.3. Yep. That's exactly what they say. Again, 2 different conversions for that. It's exactly how it would set that up. It's 15. I talked about 22. Let's talk about 24. So length of the pencil. Oh, yay, more. So I see it's near that one. Pretty close to that one. Sorry. 7.2, 7.4, 7.6, 7.8, 8. Yeah, so I would say that's 7.2-ish. And again, they're reporting that it's exactly 7.2. As far as I can tell, that's exactly 7.2. Yes. Again, it is an estimate. So if you think that's a little over, I can see why you might think that, but I would report that as 7.2. That's just my feeling on it. And again, if I were doing this in reality, I would line up a piece of paper between the ruler mark and the pencil to see where it lines up. Just to see how it lines up. So, because that's the best magnification they'll give me for that. So, it's not that easy to do, but that's how that works. All right. Take a look at 26. So 2.8 times 10 to the 7th mole per kilogram times meter squared. And they want that in mole over gram times centimeter squared. Okay, so I'm going to do the kilogram first because I want to go from 1 kilogram to 1,000 grams. So that's that one. Cancels the kilograms, supposed to be in grams. Now the other thing I have to do is that I know that there's 1 meter and there are 100 centimeters in that 1 meter. Now I've got to square the whole thing. If I square this whole thing, that means I have a meter squared on the top and 100 centimeters cubed on the bottom, or squared on the bottom. So I have to square the whole thing. And when I square that whole thing, oh, for the love of God, you can't see that. I'm sorry. When I square this whole thing, what happens is that 100 ends up being squared. And so that number comes out to be 2.8 times 10 to the 7th mole per kilogram times meters squared. 1 kilogram over 1,000 grams times 1 meter squared over 1,000,000 centimeters squared. And so this meter squared cancels with the meter squared here, the kilogram squared, kilogram cancels with the kilogram, and it leaves you with mole over gram times centimeter cubed, centimeter squared, which is what they're looking for. So now I can do my happy math, 2.8 second E here. 2.8 second E to the 7th divided by 1,000 divided by 1, 0, 0, 0, 0. And it gives me 2.8. No exponent, so 2.8, which is exactly what they're reporting. Okay. And again, it's making sure that you do whatever you do for that unit. So if you want to square that whole thing, you got to square the number as well. Okay. So make sure that you take care of that, whatever you do to the unit, you have to do the number. That's why I'm having you do that, is to make sure that you're treating them both the same way. Okay. So that's one. This. That was 26. And we want to talk about 27. Let's talk about 27. Oh, hooray! Decide whether each proposed multiplication or division of measurements is possible. If it is possible, write the result in the last column of the table. Okay. So 3.0 grams squared times 4 grams. Yes, it's possible. And we're going to take 3 times 4, which is going to be 12, and it's going to be grams cubed. So grams squared times grams is going to be grams cubed. 56 divided by 7 is going to give me 56 divided by 7 is going to be 8, and that's going to be grams per centimeter cubed. So that is possible. Absolutely it is. And here we're going to have 2 grams squared times 0.3 kilograms. Well, I'm going to have to change one of those, and it probably doesn't matter which one I do. So I'm going to go ahead and change this one. So I'm going to take that 0. .033 times 1,000 to get everything into grams, and then multiply that by 2. And it gives me 6.6 times 10 to the first, and that is in grams cubed. So that was possible as well. And 66. So 8 and 12. Yep. So yeah, I mean, there are very few of these that we can't do. The question becomes, can we do them without changing the units? Most of the time the answer is yes, but when we have something that's in grams and kilograms, we're gonna have to change one of them. And that's something we have to worry about. So. Okay, cool with that? Oh, excuse me. Again, the point of this was not to force you into a formula, into doing anything in particular. The point of this was to force you to work with the units. So I wanted you to think about, what are these units, okay? And to work with the exam handouts that you have. So what you've been given on for those exam handouts to say, okay, what do these things look like? You know, what's the relationship between the regular unit and, you know, the kilo, so that's 10 to the third. What's, you know, the deci, which is 10 to the minus 1, you know, the centi, which is 10 to the minus 2. You know, how do I do those conversions so that you start becoming comfortable with using that? Okay, because it's going to become very important as we continue to do this, is you're going to have to be able to work with those prefixes to get things converted. Okay, that becomes important. We're going to have to, you know, eventually we're going to be working with other conversions, so that we're going to be changing from meters to inches to feet, you know, inches to centimeters. You know, all of these things are going to become important at some point in time. We're going to do temperature conversions when we get to the gases. So understanding how to do those conversions and how they work is really an important part of what we do in this class. And keeping these numbers with their units with them becomes really important. So I hope that helped, and I hope that made sense. I am going to send a copy of this workbook that I did to you, and hopefully that will help. I know my handwriting is messy, so I know it may not help, but I will be able to PDF this and send it to you along with this video. So I will get that to you as soon as I can. And again, hopefully this was helpful. If it was not, or if you need additional help, please let me know. And I am more than happy to get that done as soon as I can. So hopefully it won't take as long the next time I have to do this. So again, thanks. I will talk to you soon. Okay, bye.